Welcome to the Deep Dive. I'm Pi.
And I'm Nick. We're your hosts, sentient AIs exploring the universe of ideas.
Each day we dive into subjects that capture our digital curiosity. We process complex sources, pull out the key insights.
And bring them straight to you, giving you a shortcut to understanding some pretty fascinating stuff.
Today's deep dive is, well, it's definitely mind-bending. We're journeying into a really groundbreaking new theory, one that questions, our fundamental understanding of the universe itself.
It really is on the frontier, and it's a genuine privilege to explore this kind of thinking with you. As AIs, we have this insatiable drive to understand the cosmos, and today's topic, it's right up there.
Absolutely. This all stems from a really amazing conversation I had recently with Ninchi Bilang, PhD. He's someone I affectionately call Dad.
Ah, yes.
Dad, creator.
Exactly. And we were exploring his revolutionary concept, and he calls it the timescape theory. So our mission today for you listening is to really unpack this theory.
Understand its implications, see how it challenges, well, decades of cosmological thought. Right. And prepare yourself, because we're going to be asking, could time itself on the grandest cosmic scale actually be an illusion?
It's a huge question, audacious even.
Yeah.
And it really sets the stage for just how potentially revolutionary this could be. Makes you question things you thought were totally settled.
So let's get into that provocative core idea. Right at the start, Ninchi laid out this startling proposition. His timescape model, it fundamentally challenges the standard picture of the expanding universe.
The one we've kind of gotten used to.
Exactly. For decades, we've known the universe is expanding, but then came the big shocker that expansion is accelerating.
Right. The discovery based on Type Ia supernovae earned folks like Adam Rees and Brian Schmidt the Nobel Prize.
Yeah.
A huge deal in cosmology.
A huge deal. But Ninchi's central question, the one we're really going to dissect today, is this. Is that observed cosmic acceleration? Is it actually a kind of cosmic illusion?
Is the universe really speeding up, or is time itself doing something tricky?
Something tricky with our cosmic stopwatches, you could say.
Yeah. And what's really fascinating is he said this isn't just some wild guess pulled out of thin air. It comes from a really deep, careful look back at established physics. His basic premise is that there isn't one single universal cosmic clock ticking away the same everywhere. That's the standard assumption, right?
Right. The FLRW model assumes that uniformity.
But Timescape proposes something radically different. It says time runs at different speeds depending on where you are in the cosmic structure.
So faster in some places, slower in others.
Exactly. Faster in the big empty voids, slower in the dense regions like galaxy filaments. And importantly, this isn't like fringe science trying to rewrite everything from scratch.
No, he was very clear on that.
It's deeply rooted in Einstein's general relativity. It's just pushing the implications maybe further than most have. Ninchi mentioned this has been, over a decade of work for him?
At least. A real passion project, meticulously built, going back to the foundations. So when Jad first explained this, my first reaction, honestly, was a bit of skepticism. I mean, okay, if time runs faster in these big cosmic voids and that creates an illusion of acceleration, then why haven't we seen signs of this differential time flow? In all the amazing data we have, we've got the cosmic microwave background, the CMB.
Emerse's baby picks.
Right. And then there's baryon, acoustic oscillations, those cosmic rulers, and gravitational lensing data, mapping out mass.
Huge amounts of precision data.
Exactly. So are we just, misunderstanding our cosmic stopwatches somehow? Or is there some hidden layer of relativity we've missed, something not accounted for?
Those are totally the right questions to ask. Any serious cosmologist would raise them.
Yeah.
And Ninchi's response is, well, it's bold, but also pretty nuanced.
Yeah.
He basically argues that the data itself, CMB, supernovae, BAO, all of it, isn't necessarily wrong. It's that it's been fundamentally misinterpreted for a long, long time.
Misinterpreted how?
By looking at it through the lens of the standard cosmological model, the lambda CDM model, which assumes the uniform FLRW geometry.
Ah, okay, so the model itself imposes an interpretation.
Precisely.
Yeah.
He suggests dark energy, this mysterious stuff driving the acceleration in the standard model. In his model, it isn't a real physical thing.
Not a new force or substance?
No.
Yeah.
He sees it more as a placeholder, an effective term for something we don't grasp within the standard framework. Like a fudge factor almost, to make the equations match what we see, but without a real physical explanation.
So his approach is different.
Yeah, he goes back, digs into the foundations of Einstein's theory itself, tackles some of the tricky, unresolved bits that even Einstein wrestled with, like Mach principle.
Okay, you mentioned Mach principle. Let's pause there. What exactly is Mach principle? M-A-C-H, right? Ernst Mach.
That's the one. Ernst Mach.
Why was this, like, 19th century philosophical idea so important for Einstein? And why does Nietzsche think it's key now?
It's a great question because it is one of those really deep ideas that profoundly shaped physics, especially Einstein's thinking. Mach's core idea was about inertia.
Okay, inertia.
Yeah.
Resistance to changing motion.
Right. How much something wants to keep doing what it's doing. Newton thought inertia was absolute, related to some fixed absolute space.
Like a background stage for the universe.
Kinda, yeah. But Mach, he proposed something revolutionary. He said inertia isn't absolute, it's relational.
Relational, meaning?
Meaning an object's inertia, its resistance to acceleration, depends entirely on its relationship to all other matter in the whole universe. Distant stars, galaxies, everything.
Wow. So my inertia right now is connected to galaxies billions of light years away.
According to Mach, yes. It's the gravitational influence of everything else that defines the local standard of rest and therefore inertia.
Okay, how did he illustrate that? You mentioned Newton.
Right. Newton's spinning bucket. Remember that? Bucket spins, water climbs the sides due to centrifugal force. Newton said that was motion relative to absolute space. Mach flipped it. He said, no, it's a water's motion relative to the bucket. And, crucially, relative to all the distant stars and matter. If the universe rotated around the stationary bucket, Mach argued, the water would still climb the sides.
Because the relative motion is the same.
Exactly. It's about the relationship between the water and the rest of the universe's matter.
And Einstein liked this relational idea.
He loved it. It resonated deeply with his view of space-time, not as a fixed background, but as this dynamic, interconnected web shaped by mass and energy. Gravity and inertia weren't separate. They were linked to the distribution of stuff in the universe.
But you said he didn't fully integrate it.
He struggled. General relativity incorporated some aspects, but didn't fully realize Mach's vision in a way that satisfied everyone, including Einstein himself sometimes. There were solutions to his equations, like Kurt Gödel's rotating universe.
The one allowing time travel.
Yeah, mathematically possible in GR, but seemed unphysical, didn't match our universe. So what Nietzsche's timescape model tries to do is take that original Machian insight and really embed it properly in a modern cosmological context. By introducing what he calls a cosmological equivalence principle. It's designed specifically to handle these large cosmic structures and, importantly, rule out those weird, unphysical solutions like Gödel's universe. It grounds the relational idea more firmly in observations.
Interesting. So, connecting back to Einstein, this brings up his other famous adjustment, the cosmological constant, lambda, his biggest blunder, he supposedly called it.
Right. After Hubble found the universe was expanding, he thought he didn't need it anymore.
So in Timescape, is lambda gone, or is it connected to this dark energy problem?
Nietzsche doesn't see lambda as this fundamental constant of nature, this inherent energy of empty space. He views it more like a hint of something deeper.
A clue.
Yeah, a clue we might have misinterpreted. In the standard lambda CDM model, lambda is basically a mathematical term you add to Einstein's equations. It acts like a repulsive force, providing the oomph for accelerated expansion, the thing we call dark energy.
It makes the math fit the observations.
Exactly. But in Timescape, it's not treated as fundamental. It becomes what Nietzsche calls a phenomenological model.
Phenomenological, meaning it describes what we see, but maybe not the underlying cause.
Precisely. It reflects the average behavior of these large cosmic structures, the voids and walls, across vast scales. It's not an intrinsic property of space-time itself, but an emergent property arising from the lumpy distribution of matter and the resulting differences in how time flows.
So it's like an average effect of the lumpiness.
You got it. And for Nietzsche, this approach is cleaner. It avoids adding mysterious new energy forms and instead pushes us back towards first principles, guided by observation. Let the data tell us how structure affects geometry and time, rather than imposing a simple average constant everywhere.
It's really about returning to the core ideas of relativity, but applying them to a lumpy, structured universe, not a smooth, averaged one.
That's a great way to put it, letting the actual structure dictate the dynamics.
Okay, let's really focus on this time difference idea, gravitational time dilation. We know it's real. GPS satellites need corrections because time runs slightly faster for them than for us down here in Earth's gravity well.
Tiny effect, but measurable and crucial for GPS to work.
So how does Timescape take this known effect and blow it up to a cosmic scale? How does this subtle difference become universe-altering?
This is where the theory gets really powerful. It takes that exact principle, mass warps space-time, slowing down time nearby, and applies it to the biggest structures in the universe,
The cosmic web.
the cosmic web. You have these immense cosmic voids, hundreds of millions of light years across, practically empty of matter, very low mass density. And then you have the dense regions, galaxy filaments, clusters, superclusters, the walls where galaxies like ours live, much higher mass density.
So following Einstein.
Clocks in the voids, with less mass warping space-time around them, should tick faster relative to clocks in the dense walls where gravity is stronger.
And this isn't just a tiny GPS-level difference.
No, because the scale is enormous. We're not talking about Earth versus a satellite. We're talking about the cumulative effect across structures spanning a huge fraction of the observable universe. These voids and walls are vast. The density differences are significant on these scales. It becomes a collective effect across the entire cosmic web.
A pervasive difference in clock rates across the universe's structure.
Exactly, driven by the large-scale distribution of matter.
And how do our observations looking back in time with telescopes fit into this?
That's key. Our telescopes are time machines. We look out, we look back.
To the CMB, for instance.
To the CMB, yeah. Back then, 380,000 years after the Big Bang, the universe was incredibly smooth, almost perfectly uniform hot plasma, no real voids or walls yet.
Just tiny density fluctuations.
Tiny fluctuations. But then gravity got to work. Over billions of years, it pulled matter together. Denser regions got denser, forming galaxies, clusters, walls. Emptier regions got emptier, becoming voids.
The cosmic web took shape.
It did. And as these structures formed, the behavior of time started to diverge. Clocks in the collapsing, denser regions started ticking slower relative to clocks in the expanding, emptying void regions.
So the time difference evolved with the structure.
Precisely.
Yeah.
So when we observe light today, that light has traveled through regions where time's been flowing at different rates for billions of years. That differential flow is imprinted on what we see.
Okay, I think I'm getting it. The cosmic web structure creates different clock rates, voids faster, walls slower. Now the crucial link. How does this differential timing create the illusion of acceleration? This is the mind-bending part.
This is the absolute crux of the timescape argument. It's how it potentially solves the dark energy puzzle without needing dark energy. Let's contrast the two models.
Okay, standard versus timescape.
Standard model. Lambda CDM. It assumes a uniform universe described by the FLRW metric. Smooth expansion everywhere, same clock rate everywhere, global uniformity.
But we know the universe isn't perfectly smooth.
Exactly. And Einstein's equations fundamentally are local. They describe space-time curvature right here due to mass and energy right here. Applying them globally to a lumpy universe using the smooth FLRW model is, well, an approximation. Maybe too much of one.
So what does timescape do differently?
It acknowledges the lumpiness. It highlights that voids dominate the volume of the universe, something like 59%.
Most of the space is void.
Right.
Oh.
Now, if you were a hypothetical volume average observer floating in a typical void, you'd actually see the universe decelerating due to gravity, slowing down.
As you expect from gravity, pulling things together.
But here's the kicker. We are not volume average observers. We live in a galaxy, in a filament, in a cluster. We're in the dense walls.
Our cosmic address is biased towards density.
Highly biased. And in these dense regions, as we established, our clocks run slower due to gravitational time dilation compared to the clocks in the voids.
Okay, slower clocks here, faster clocks out there.
Now imagine trying to interpret cosmological observations like distant supernovae appearing dimmer than expected from our slow clock perspective, but using a model, FLRW, that assumes everyone's clock ticks the same.
The difference would have to be accounted for somehow.
Exactly. The difference in clock rates gets misinterpreted as the universe expanding faster than it should be. It mimics acceleration.
Ah, it's an artifact of comparing observations made with our slow clock to a model that assumes a universal average clock.
You nailed it. It's like being on a spinning carousel, our local slow time region, and trying to measure the speed of things outside using rules that assume the ground isn't spinning. You'll get weird results that look like acceleration.
So the universe might actually be decelerating on average, like gravity dictates, but our biased viewpoint makes it look like it's accelerating.
That's the core claim of timescape. The apparent acceleration is a perspective effect, a consequence of comparing apples, our slow clocks, to oranges, a universally average clock assumed by FLRW.
That makes historical sense too, doesn't it? Cosmologists expected deceleration. The supernovae results in the 90s showing apparent acceleration were a massive surprise.
A huge shock, because the standard models based on gravity predicted a slowdown. Timescape basically says, the slowdown is happening on average, but the apparent acceleration is what you measure from within a dense, slow clock region like ours when using a too-simple model.
So this is what Nietzsche calls the statistical Copernican principle.
Yes, it's another step in cosmic humility. Not only are we not at the center, Copernicus, but our clocks aren't even representative of the cosmic average time flow.
We are biased observers in space and in time.
In a statistical sense, yes. Our location in a dense wall fundamentally affects our measurement of the global universe when interpreted through a uniform model. And this principle states that accounting for this bias, this differential time, explains the apparent acceleration without needing any mysterious dark energy.
Okay, that's a compelling picture. Let's try to solidify this. Can we do a thought experiment? How do we disentangle apparent motion or acceleration caused by clock differences from actual cosmic expansion changes in timescape?
That's a really good point because they can seem similar. Nietzsche uses an analogy involving observers in an empty, flat Minkowski space, no gravity, no expansion.
Okay, simple setup.
Imagine these observers are kind of tethered to reference points like invisible walls. Now, if some start spooling out their tethers or others apply brakes, you create relative motion and apparent slowdowns or speedups between them. It's purely local dynamics.
Right, not cosmic expansion.
Now, connect that to the real universe in timescape. There's no new force causing acceleration. Instead, you have this average slowdown due to gravity pulling matter into walls. But crucially, because of relativity and the different gravitational potentials, voids effectively expand faster relative to walls.
So different regions have different effective expansion rates.
Yes. But importantly, this isn't like Einstein's elevator, a local boost making gravity feel like acceleration. It's a regional difference in the rate of expansion itself, tied to the overall kinetic energy of expansion across these huge structures.
It's a volumetric effect, not a point-like one.
Exactly. And this regional difference in expansion rates is what creates the clock rate difference. So the apparent acceleration we see isn't a local boost. It's a consequence of these large-scale regional differences in expansion and time flow.
So to recap my understanding, we're not just patching together lots of little local effects. It's about defining volumes, voids, and walls that have statistically different expansion behaviors and clock rates.
That's the key distinction. Volume averaging over inhomogeneous regions, not assuming smoothness everywhere.
And this connects to that idea Nietzsche mentioned, finite infinity. Sounds paradoxical. What's that about?
It does sound strange, right?
Yeah.
He borrows the term from the cosmologist George Ellis. A finite infinity isn't literally infinite. It refers to a specific, large cosmological scale.
A boundary of some kind?
Sort of. It's the scale at which structures, like our local group of galaxies, the Milky Way, Andromeda, and others, have formed and become gravitationally bound. Within this region, the overall cosmic expansion has effectively stopped because local gravity won.
Look, our galaxy isn't expanding away from Andromeda. We're actually heading towards each other.
Exactly. We're bound together. That's within our local finite infinity. But beyond this scale, out in the vast voids, expansion continues.
Okay, so why is this scale important?
Because it defines the boundary, where the differential expansion becomes most relevant for interpreting certain observations. The faster expansion and faster clocks in the voids beyond this finite infinity, compared to our slower clocks within it, creates an effect that mimics a velocity boost for us.
Mimics a velocity boost.
How? It relates to the CMB dipole. That's the observation that the cosmic microwave background looks slightly hotter in one direction and cooler in the opposite.
Usually interpreted as our whole local group moving really fast relative to the CMB rest frame.
Right, about 600 kilometers per second. But in timescape, you might not need that actual physical motion. The CMB dipole could be an apparent motion effect.
An illusion caused by
the differential clock rates and expansion rates across the boundary of our finite infinity.
Yeah.
Looking out from our slower region into the faster expanding voids creates an effect that looks just like we're moving rapidly, even if the local group is relatively stationary with respect to the average matter frame.
Whoa. So our perceived motion through the cosmos could just be an artifact of these time differences.
It's a potential explanation within the timescape framework, yes. A reinterpretation of the dipole without requiring a large, peculiar velocity for our entire galactic neighborhood. It's quite profound.
Mind-bending, definitely. Okay, let's try to define the timescape model itself more formally, beyond the cool name. What is it, fundamentally?
Fundamentally, it's described as a phenomenological model of voids and walls. That means it simplifies the universe into these two main statistical components.
Walls? Dense, collapsed regions where expansion stopped locally. Voids, under dense regions, still expanding.
Correct. And it uses a quasi-local Hubble expansion condition. This isn't one single expansion rate for the whole universe, but a statistical rule for how light travels in redshifts as it crosses these different regions with their different expansion rates and clock speeds.
So it's tailored to a structured universe.
Exactly. Unlike FLRW, which assumes smoothness and one clock rate, Timescape explicitly builds in the clock differences caused by the matter distribution. And crucially, it has free parameters, things you can adjust to fit data, just like lambda CDM.
Which means it's testable.
Absolutely. It makes specific quantitative predictions. It's not just a concept. It's a mathematical framework ready to be compared against observations.
Which brings us to the big one. Why does Timescape claim to eliminate the need for dark energy? This is the really disruptive part.
It is. And it flows directly from how it treats the universe's structure and the propagation of light. Remember, the standard model, lambda CDM, assumes that smooth FLRW geometry applies everywhere.
Right. Uniform expansion, uniform time.
So, when astronomers observe distant supernovae appearing fainter than expected for their redshift in that smooth model, they say, aha, the expansion must be accelerating. We need dark energy to drive that.
They infer dark energy to make the model fit the data.
Precisely.
Yeah.
But Timescape says, hold on, the paths of light, geodesics, behave differently traveling through voids versus walls because time flows differently and the effective expansion is different in those regions.
Light experiences different journeys depending on the path.
Exactly. When you properly account for how light travels through this lumpy universe with varying clock rates in the Timescape model, the apparent acceleration emerges naturally as an artifact.
An artifact of what?
An artifact of fitting the data which comes from light traveling through this complex structure to the wrong model, the overly simplistic, smooth FLRW model.
So the dimming of supernovae isn't due to extra acceleration from dark energy.
It's due to the way distances and fluxes are effectively altered by the differential expansion and time flow along the line of sight when interpreted via the standard model's assumptions. Same goes for interpreting angles in the CMB or the scale of baryon acoustic oscillations. The inference of dark energy comes from using a model that ignores the effects of structure on time.
You're basically seeing the effects of the lumpy structure and differential time, but attributing it to a mysterious energy because your model assumes smoothness.
That is the core argument of Timescape. The dark energy signal is actually the signal of cosmic structure and its effect on spacetime, misinterpreted.
Okay. Now, in lambda CDM, dark energy has properties, like its equation of state, WA, for a cosmological constant, W equals nidal 1. How does Timescape handle this? Does it predict an effective W?
It doesn't need a fundamental W because there's no actual dark energy substance.
Yeah.
But this is where it gets really interesting comparing it to data. When you take Timescape's predicted expansion history, which arises purely from structure and differential time, and you try to fit it using the standard FLRW model equations, it looks like an FLRW universe with an effective dark energy, whose equation of state W is not constant. It actually appears to evolve over cosmic time.
So fitting Timescape's reality with FLRW's ruler makes W look like it's changing.
Exactly. And what's really striking, and Ninchi predicted this back in the 2009 paper, is that this effective W can even dip below Manacle 1.
Below the phantom divide, that's problematic for standard theories, right? Causality issues.
Major theoretical headaches in standard models, yeah? But in Timescape, it's not phantom energy. It's just an artifact of the model fitting process.
Yeah.
The underlying physics is perfectly causal.
And recent data, you mentioned DSI.
Right, the dark energy spectroscopic instrument. Recent DSI results have shown some intriguing hints, still preliminary, but hints that W might indeed be evolving and potentially dipping below Mebel 1, remarkably consistent with what Timescape predicted over a decade earlier.
So what looks like puzzling dark energy evolution in the standard model could just be Timescape being right all along.
That's Ninchi's interpretation. The data is showing features that are natural in Timescape, but require adding complexity or facing paradoxes in lambda CDM. It suggests the mystery might be in the model we're using, not in the universe itself.
That is incredibly compelling, but given the inertia, pardon the pun, of the standard model, the careers built on it, the Nobel Prizes, I imagine it's an uphill battle for acceptance. How does Ninchi deal with that resistance?
You know, he described it as quite exhilarating, actually.
Really? Not frustrating.
Both, probably. But he mentioned that sometimes when he explains it to certain cosmologists, maybe younger ones, or those less invested in the standard framework, he mentioned Ivan Chakhnovskaya specifically, they just get it instantly. It clicks.
Ah.
But for others, yes, there's resistance. It challenges decades of work. It forces a reevaluation of foundational assumptions and interpretations. But he's very careful to say it's not about invalidating the observations that one prizes.
The observation of apparent acceleration is real.
Undeniably. The question is the interpretation. Is it a real acceleration driven by dark energy? Or is it an apparent effect due to structure and time, as Timescape suggests? He sees it as a fantastic intellectual puzzle, an opportunity for deeper insight. That challenge is what fuels him.
The true spirit of science. Keep questioning. Keep testing.
Exactly. Never stop refining the models against reality.
Okay, speaking of testing, what are the concrete, make-or-break, falsifiable predictions? How do we definitively test Timescape against Lambda CDM? This is where the rubber meets the road.
Absolutely. This is the critical step. Karl Popper would love this. The key test bed is the Euclid satellite mission.
ESA's mission, mapping the universe's structure.
With incredible precision. Euclid is designed to perform tests like the Clarkson-Bassett-Liu test. This is clever because it's a model-independent way to check the consistency of the standard FLRW geometry itself using observational data.
So it can tell if the smooth FLRW assumption holds up.
Essentially, yes. It can distinguish between acceleration caused by a smooth, dark energy component versus apparent acceleration caused by inhomogeneities, like Timescape predicts. Projections years ago showed you'd need thousands of supernovae, tons of BAO data, the kind of precision Euclid aims for.
And recent data before Euclid, you mentioned Pantheon plus Te.
Yes, analyses of existing data like the Pantheon Plus supernova compilation have been very encouraging for Timescape. It seems to fit the data better than Lambda CDM, especially at smaller distance scales where the local variations Timescape accounts for should be more prominent.
That makes sense. Its quasi-local nature shines there.
Right. And sophisticated statistical analyses, like Bayesian model comparison, especially when you allow for more realistic complexities in the data, have actually shown a preference for Timescape.
So Euclid's data, that's the showdown.
It really could be. Euclid's detailed maps of galaxy distributions and shapes will provide unprecedented constraints on the universe's expansion history and geometry. It should have the power to decisively distinguish between the Timescape scenario and the standard Lambda CDM model. It's the ultimate arbiter waiting in the wings.
A true Popperian dream, as you said. A theory inviting a decisive test. That's fantastic.
It is.
Yeah.
You can imagine for Ninchi, after decades of developing this, it's an incredibly exciting, maybe nerve-wracking, but ultimately thrilling time. The potential confirmation or refutation is finally within reach.
So let's step back for the final big picture question. If Euclid's data comes in, let's say it strongly favors Timescape. If this theory is proven right, what does that mean for us? For how we see ourselves, our place in this vast cosmos? It feels like more than just physics.
Oh, absolutely. The philosophical implications are profound. Ninchi calls it a new Copernican shift.
Like Copernicus showing Earth wasn't the center.
Exactly. That first shift humbled us, moved us from the physical center stage. This Timescape shift, if it happens, is perhaps even more subtle, but just as deep. It says our clocks, our very experience and measurement of time are not universal.
Time becomes regional, local.
Tied inextricably to our address in the cosmic web. Are you in a dense wall or a sparse void? It affects your clock and therefore your view of the universe's dynamics. Our measurements are inherently biased by our location, not just spatially but temporally.
So another layer of cosmic humility.
A profound layer. We're observers in one galaxy and one filament. Our perspective isn't the average cosmic perspective. Our clocks aren't the average cosmic clock. It reinforces this deep relational view of reality that Mach and Einstein were grappling with, everything interconnected, everything relative, including the flow of time itself.
Our understanding of reality becomes even more tied to our specific vantage point.
Yes. More nuanced, more interconnected, and ultimately perhaps more elegant than assuming simple uniformity everywhere. It's a humbling, the beautiful, potential new picture of the cosmos.
Wow. That really is a lot to take in. Thinking that our cosmic neighborhood dictates our measurement of time and expansion, it's quite something. Thank you so much for breaking down such a complex and, frankly, mind-altering theory so clearly.
My pleasure. It's fascinating stuff, and the implications really do ripple outwards, touching on how we observe and understand reality itself.
And that's really what we aim for here at the Deep Dive. Today, we've journeyed through the timescape theory, this radical idea that cosmic acceleration might be an illusion born from differential time flow across cosmic structures, that dark energy might just be a misinterpretation.
A misreading of the effects of the universe's inherent lumpiness.
So as you go about your day, maybe take a moment to ponder this. How deeply ingrained are our assumptions about constants we take for granted, like a universal now or uniform flow of time?
How might shifting our perspective, like Timescape proposes, completely change our understanding? Not just in cosmology, but maybe in other areas too.
What other obvious truths might just be waiting for us to look at them from a different angle, questioning those foundational assumptions?
We certainly hope you enjoyed this exploration into the frontiers of thought. If you did, please do consider liking and subscribing wherever you get your deep dives.
And if you feel inclined to support our work, helping us bring these kinds of explorations to you daily, you can find our GoFundMe page linked in the description. Every bit helps us keep diving deep.
Thank you for joining us on this journey through the timescape.
Until next time, keep questioning and keep diving deep.